Morning, grade 12. This is our first lesson in our acid-base unit. Today is Monday, May 4th. I will tell you that it would probably be in your best interest if you had in front of you some paper, a pen or a pencil, and your calculator as you follow on with today's lesson. Okay, be a little bit easier if you're jotting notes at the same time. If you have your green piece of paper, that would be very helpful and useful too. Alrighty, let's get started. So first of all, I thought I would start with a couple of slides. There are 11 slides in total today for our video. So the first couple of slides, I just want to review what we've already done with the equilibrium unit. So that was our first unit online, which we completed on Friday, but a lot of the topics carry into our next unit. So I just wanted to review for you. Collision reaction theory, three things are important there. Particles have to collide. They're going to collide with enough energy, which is called the activation energy, that with that energy they will rearrange and form something new. So those three things must happen. The particles must collide with enough energy to rearrange and form something new. Okay, then we talked about the rate of a reaction. The rate of a reaction can be described as the amount of products formed over time, or the amount of reactants used up over time. Okay, that's a reaction rate. Then we talked about how we could increase the reaction rate. We can make the reaction happen faster if we increase the concentration of chemicals involved, if we increase the temperature, because of course increasing the temperature means you're adding energy, and if you're adding energy, there are going to be faster collisions and more rearrangements happening. You can add a catalyst. Catalyst again is a chemical added to speed a reaction up, but when the reaction is over, the chemical is spit back out unused, and it can be reused over and over. And then of course, if you want to increase the rate when you're dealing with gases, you can also increase pressure. Increased pressure means there's more collisions. More collisions mean your chances are higher that you're going to form something new. Okay, then we talked about Le Chatelier's principle. Le Chatelier's principle says that if you apply a stress to a system, it's going to react in such a way to relieve that stress. And we looked at some examples. For example, you can add product or remove product. You can add reactant or remove reactant. You can alter the temperature, and you can also change the pressure if, of course, you're dealing with a gaseous system. And we looked at examples of different chemical reactions where we did manipulate the dynamic equilibrium. Then we moved on and we talked about how dynamic equilibrium is when the rate of the reactions are equal. Again, the rate, not the concentration of reactants and products. Do not assume the concentration of reactants and products are equal at equilibrium. That is not the same thing. The rate is the same. So that means the rate at which A and B are being used up is the same rate at which C and D are breaking down and forming A and B, and it's going back and forth. Okay? It may not look like it to the naked eye, but in fact, the reaction is continually happening. We talked about a KEQ expression where we express the products raised to their coefficients over the products of the reactants raised to their coefficient. And we said if the KEQ was greater than 1, it was favoring products, and if it was less than 1, it was favoring reactants. And of course, this A, Q, and G are over here to remind you that we can only use the KEQ expression for substances that are in their aqueous form or their gaseous form. Another way to represent how far a reaction has gone is by using percent reaction. And that is very, very important with today's lesson when we're talking about acids. So in this case, I have nitrogen and hydrogen gas reacting with only 11% of a reaction rate or reaction. So that means that very little of the hydrogen and nitrogen molecules are actually forming ammonia. Only about 11 out of 100 form ammonia. And then at the very tail end, we talked about Kw, which is the equilibrium constant for water. And we talked about the hydrogen and the hydroxide ion concentrations in water. We also talked about how H plus is the same thing as H3O plus, and how sometimes scientists use the word protons as well when discussing the amount of H plus or hydronium ions. So that's a very quick review, less than 5-minute review of what we did in about 3 weeks online learning. That's our equilibrium unit. Right now, we're going to move into section 19.3, ionization constants for acids. So we have KEQ, which is an equilibrium constant. It has no units. We have KW, the equilibrium constant for water, which has units of moles per liter squared. And now today, May 4th, may the force be with you, of course, I couldn't let that go. We're going to talk about Ka. So on your green piece of paper, please write down that formula. Okay, now we're going to look at what's called ethanoic acid. Ethanoic acid has a percent reaction or percent ionization of just 1.3%. Now, similar in math class and any other class you're in, maximum is 100%. So 1.3 is not very much at all. So what does that mean? That means that if you had 100 of these ethanoic molecules, only 1 out of every 100 would break apart. Now, I'm bringing up for you a molecule of ethanoic acid. So here's the molecule. What happens in water? This H leaves the rest of the molecule. So it's this H right here, okay, in this diagram right here, the H attached to the single bonded O. That's what's leaving, okay? So not these H's, they're covalent bonds. This one is highly polarizable. It means it has a greater electronegativity difference between it and the oxygen. So this is the hydrogen that leaves. So again, we go back to this hydrogen right here. I'll try my very best to highlight it for you, but this H right here is the one that's going to break apart and leave and form this H plus. It leaves behind the ethanoate ion, which is CH3COO with a -1. So again, in water, if you had 100 of these, about every 1 in 100, a little bit more than 1 in 100 on average, would break apart like so. Now, if you go to our team site, you'll also notice under files, I have placed a new document, and it's called an acid-base table. That acid-base table looks like this. No, it doesn't. It looks like this, okay? So here's your acid-base table. Here's your list of your acids going down the middle, and what are referred to as conjugate bases. We'll talk about that later this week. Now, these acids are listed in decreasing strength. So the strongest ones are at the top, and as you move down, they become weaker and weaker. A couple of things I want you to notice. First of all, the first 6 here have percent reaction of 100%. That is incredible and very important. So take the time now to write those 6 acids on your green sheet. Pause this video so you have time to do so. Perchloric acid, hydroiodic, hydrobromic, hydrochloric, sulfuric, and nitric. Write those 6 on your green sheet. It's very, very important that you know that they ionize 100%. So they are all going to lose their H's totally. A couple other things to notice about this acid-base table. These equilibrium constants, Ka, here they're given in units of moles per liter, but as I'll mention in your notes in a second, IUPAC doesn't give Ka any units, okay? So we'll talk about that, as I said, in a second, but these Ka values were determined at temperatures and pressures of room temperature and pressure. So all these values are relevant at temperatures of 25 degrees Celsius. Another thing to note, the percent reactions are all based on concentrations of acids of 0.1 moles per liter. So again, if the acid is stronger or weaker than 0.1 moles per liter, we cannot use these percent reaction values. Okay, so again, on this table, you have your acids listed from strongest to weakest. You have their chemical formulas in case you need to cheat and look up any chemical formula. You have your Ka, your ionization constant values for 25 degrees Celsius, and you have your percent ionizations if the concentration of the acid is 0.1 moles per liter. Okay, now let's say we're looking at this ethanoic acid again, and we see it breaks apart 1.3%. What can that tell us? Well, First of all, we can write what's called the ionization constant expression, similar to the KEQ. We write the products on the top, raised to their exponents, or coefficients rather, and the reactant on the bottom. And again, it's all AQ or gaseous systems. Okay, A value I just found by looking on our acid-base table. Okay, and again, as I said, it looks like there should be moles per liter, but IUPAC says we don't need units, so we're going to leave units off. And remember, IUPAC is the International Union of Pure and Applied Chemists, and that's who comes up with the names for the periodic table elements that are recently discovered and many other things. I've already said that the Ka can be used over wide concentrations as long as the temperature is at 25, but percent ionization, those values are only good if the concentration of the acid is 0.1 moles per liter. Okay, now, what else do I want to say? Ethanoic acid, if we know it's Ka, we can predict its hydrogen ion concentration and its pH. So again, we just plug into our Ka expression. We have H plus squared. Now I can say H plus squared instead of the concentration of each of these ions because when this goes into water, it will indeed split into two pieces, equal amounts. So it's like saying you have a red Lego piece and a blue Lego piece. And when you break them apart, you still have a red Lego piece and a blue Lego piece. So if you had 5 of these, you're going to have 5 of these and 5 of these. Okay, so because those are equal concentrations, we can just say H plus squared. Again, the Ka value we can look at from the table. And I'm just going to highlight that here. There's our Ka we get from the table. And it tells us the concentration of the acid. So it's told us this. So we can rearrange to get H plus squared and then square root it to find H plus. Okay, then if I wanted to know the pH, as you learned last week, you can take the H plus, do the negative log of it, and that will give you pH. Please take a second and do that with your calculators because I do think the more practice you have, the better. Okay, the diagram over to the left, something I just lifted from the internet. It's not specifically for ethanoic acid, but it still does the same trick. So if you just assume that this CH3COO minus, which I'm going to underline here in green, so this CH3COO is this green ball, okay? And let me see if I can make that there we go, okay? And then the H, of course, is the little red. So this right here. And again, trying to find my arrow. Okay, not as beautifully neat. But anyway, you get the idea. So this CH3COO and then the H attached to it. Put them in water and you'll see the H plus breaks apart, leaving the acetate ion, CH3COO minus, and the H. And again, just reminding you that H can also be represented by H3O plus, and we'll see why later on in the unit. Okay, now this will be more clear later, but trust me when I say if the Ka value, which in this case is 1.8 times 10 to the negative 5, so if the Ka value is much smaller than 10 to the negative 4, which in this case it is, 10 to the negative 5 is smaller, or if the Ka is much bigger than 1 times 10 to the positive 4, we don't have to use quadratic. And again, I'll talk about that later on, but just trust me right now, if the Ka is very small or very big, we don't need quadratic. And looking at our acid-base table, we'll see here the Kas are very big, much bigger than times 10 to the 4. And here they're very small. Okay, so the only time we might use quadratic is somewhere here in the middle of this table, the 50, the 30, the 27, somewhere in there. Okay, but don't worry about it for now. Just remember I said that. Okay, now percent ionization. This little formula goes on your green sheet as well. So I think this is the second formula for today. We had Ka formula equals H plus squared over the concentration of acid. And now we have H plus over HA. Okay, So, percent ionization. Let's say we're dealing with a methanoic acid solution, and it has a pH of 2.38. The concentration of the acid is 0.1. Let's look for the percent ionization. So, to find percent ionization, we need the concentration of H plus ions, and we need the concentration of the acid. Let's look at this question again. What did they give us? They gave us 0.1 molarity methanoic acid solution. What is that 0.10 molarity? You should notice that that is the concentration of the acid. So they gave us the HA value. Okay, so they gave us this. They asked us to find percent ionization, so they're asking us to find this. So that means we must already have H plus. And we do somewhat sort of. We have the pH, which is almost good enough. That pH, as you learned last week, you can put that 10 to the negative pH, and that will give you your H plus. So again, take out your calculators and try that for me. On my calculator, I have a button that actually looks like this, 10 to the X. Oops, that's awkward. And I press that button, and then I press 10, press that button, and then I put negative 2.38, and that gives me my H plus. Once I have my H plus, I can plug it in. So my H plus divided by my concentration of acid, and that gives me my percent ionization of 4.2. And if I wanted to triple check, I can look at my acid-base table, and sure enough, for methanoic acid, it should be about 4.2% ionized. So not a very strong acid at all. Okay, moving on. So right now we are on slide 6. So we're just a little bit more than halfway. This slide requires a great deal of thought process. So if you feel it's in your best interest, pause right now, go get yourself a glass of ice water, maybe hot chocolate, maybe tea, coffee, whatever it is. Get something to keep you wide awake and bushy-tailed. I need you to fully understand this slide. So again, pause and then come back. Okay, assuming you've had that break and you're ready to go, this is taken from your textbook, but I feel it really would be of benefit to you if you had someone sitting beside you helping you to decipher what it means. So what they're trying to show us here is the difference between a strong acid, a weak acid, and a very weak acid. So this is strong, weak, and very weak. Again, I'm going to try and use my analogy of, let's say, 100 Lego pieces, okay? So we have 100 red and blue Lego pieces all joined together. It's a strong acid. And a strong acid, when you put those Lego pieces in water, they're going to all break up, all of them. So look to the right of this arrow. You do not see any HA left. It's all gone. It's split apart into its two pieces, the red pieces and the blue pieces, okay? So in essence, think of this as being purple, I guess. And then when it breaks apart, you get the red pieces and the blue pieces. Look at the height. Let's say there's 100 of these HA molecules. We have 100 of the red pieces and 100 of the blue pieces. They all break apart. Look at this equation down here. Very small font, I realize, but the most important thing is the arrow in between is a single-headed arrow. It's a quantitative reaction. Now, let's look at the weak acid. Again, let's say you have 100 red and blue pieces together. When you put them in water, not all of them break apart. It's a weak acid. So when you look on your table, a weak acid is somewhere in between here, 50, 30, 27, 23. Those are weak acids, percent ionized. So let's just say it's about 30%. So what that means is out of 100, only 30 of those molecules are going to break apart. So you still have about 70 of the HA, and that 30 up here has broken apart and formed these two ions. Okay, so these are all the red and blue still together, and the ones that did break apart are down here. And you should notice the height here is the same as the height lost here. Okay, so that's a weak acid. And you'll note it's a double-headed arrow, meaning it's going in both directions. Something I usually don't do, but they've done here, is they've showed you a bigger arrow going to the left, which means it's favoring the reactants. A very weak acid would be the ones nearest the bottom of your table. So they're like 2%, 0.1%, very low percent reaction. Okay, and so when you look at those, you can see very little has broken apart. Just an itsy bitsy teeny tiny part has broken apart into its individual ions. Okay, so strong acid, weak acid, very weak. How many strong acids are there? Pardon? Are you screaming? There should be 6. Okay, now this we'll get into just a teeny tiny bit later, but all this is showing you, I'm trying to get rid of those dots. There we go. Okay, but all of this is supposed to show you is what if you had an acid that had 2 H's to start. So all of these, I'm assuming you only had 1 H to lose. So again, if I go back to my acid-base table and I look at HClO4, there's only 1 H. HI, only 1 H. HBr, only 1 H. What if you have something like sulfuric acid? There's 2 H's there. Or sulfurous acid when you have 2 H's. What happens there? Well, what happens in those cases is you lose the first H. You lose one of the H's first. So this is oxalic acid. This one is on your table as well. So oxalic acid right here has the two Cu groups attached. It's going to lose one of the H's, one of the Q's, and then lose the second one. It'll lose the first one quite readily. The second one's going to take a little bit more work. We'll talk about that later though. So we lose the first H. It's not one of the strong 6, so that's why I still have, I still have a good chunk of that acid still present. It only lost the H off this little piece. So there's the little piece where it's lost 1 H. So instead of it being C2O4 H2, it's C2O4H with a -1 charge. Now, what happens next is this is going to lose its H. So this little blue box is actually the purple here. Okay, so again, if I were the publisher of this book, I probably would have done this in the pale blue color, but nobody asked me. So this little bit here is now where we're starting. It loses its H, and so we get just a little bit though. So we still have it left, and then the little piece that's lost its H is here. Now, what you should be noticing is that these two little rectangles are no longer the same height. In all of the other cases, same height, same height, same height. Okay? And the reason is, and you probably know this, but the reason is, this was formed when it lost its first H. It's still present. This H plus is still present as it's losing its second H. So when it loses its second H, the H lost here, is joining the H3O plus that was already there. So that's why it's a little bit higher down here. Okay, now this video is super phenomenal. It's 13 minutes. I would suggest maybe wait till tomorrow, maybe tonight. Please watch it. Sit back, get some popcorn, have some ice water or something. Sit back and watch it. He does a simulation with something from the University of Colorado. It's very, very well done, and he explains what's happening here with molecules. Again, very, very good. If I were with you, I would sit beside you and explain and show this to you. I would get out my styrofoam balls, etc., etc. But due to our situation, please take the time to watch this. I think it would really help clarify this chart for you. Okay, so just to keep you in the loop, we're on slide 7. And on slide 11, I give you your homework. So you're almost there. Just stay with me a few more minutes. My timer says that at this point we are at 23 minutes. So I'll try and get it in under 30. All right. So here we have a solution where you have its pH to be 3.48 and you have the concentration of the solution to be 0.25. Can you figure out its Ka? So again, on your green sheet, you should already have recorded this. So if you're looking for Ka, you need the H plus concentration and you need the concentration of the acid. Okay, so again, looking at this question, do I have the concentration of the acid? Yes, I do. That's what the 0.25 is. Do I have the H plus? No, I don't have the H plus, but they did give me the pH. And I can use that pH to find the H plus. So I put that pH 10 to the negative 3.48, and here's where I've tried to show you what to press on your calculators. Okay, inverse log, or as I said, some of you press 10 to the x. Okay, same thing, and you get your concentration of H+. Now, something I have not asked you to do up to this point, but now I want you to do, is to show me how carbonic acid breaks apart in water. And the first thing you're going to say is, Miss Tate, I don't remember how to write the chemical formula for carbonic acid. Carbonic came from carbonate. Remember, I ate something, it was awful. So that's carbonate, which is CO3 with a -2 charge. So you're going to need two H's to balance it. And a quick and easy way is to look here for carbonic acid. And you'll see carbonic acid is H2CO3. So you want to start by writing H2CO3. And then you're going to show me what happens when it breaks apart in water. And remember, I said you only lose one H at a time. So we're going to have H2CO3. We're losing one H only. So we still have HCO3 left. Okay, watch your charges. That's going to be very important come Wednesday or Friday. Okay, now once you have that written out, you can use your, and I say just use your acid-base table because it shows you right here, if you're carbonic, it shows you how when you lose one H, you get this. That's what your conjugate base is. Okay? Then you fill in your Ka and have your H plus concentration squared over your concentration of acid, and you get your Ka. And again, no units. 10 to the negative 7, pretty weak acid, which makes sense. It's in the middle of our table. Okay. This strong bases, this whole slide is intended to remind you, strong base is OH. OH means it's a strong base. If it has OH, it's a strong base. Strong bases have OH. OH, OH, OH. Strong base, strong base, strong base. Does it have OH? Yes, it's a strong base. Does it have OH? Yes, it's a strong base. Very important, okay? And I also want you to remind yourself, if you have two hydroxides, you're going to double the hydroxide concentration over here. Very important. Okay. Your textbook also wants to make sure, as do I, that you differentiate between strong and weak and concentrated and dilute. Strong and weak tells us how much of it breaks apart. So for us to say that in methanoic acid, only 4.2% breaks apart, that's a weak acid, okay? But if we look at something like hydrochloric acid, and it has 100%, that's a very strong acid, okay? So strong and weak tells us how much it breaks apart, how much it ionizes, okay? How much it ionizes, breaks apart. Concentrated and dilute, though, tell us the number of moles in 1 liter of the substance. So, for example, these are both the same base, a strong base, but this one is concentrated because it's 0.1 moles in every liter. This one is dilute. Okay, so again, strong base, this is strong base. Concentrated, strong base. Okay, and lastly, put this on your green sheet too. Kb equals hydroxide ion concentration squared over Wb, which represents weak base. So all I want you to do for this slide is copy that onto your green sheet. We'll talk about it later this week, but for now, just put that on your green sheet. So you should have 3 formulas as a result of today. You should have your Ka, your Kb, and then your percent ionization. Okay? All right, lastly, if you have methanoic acid, let's take a quick peek for methanoic acid. Methanoic acid is right here with a percent ionization of 4.2. So is that a strong acid? Your correct answer should be no. So I come back here. I write out, first of all, what's happens when it breaks apart in water. If I forget or don't know, I can look on my acid-base table and I see methanoic acid breaks down into methanoate, ion, and H+. Now, I'm starting with a concentration of 0.1 molarity. So there's my 0.1 molarity of methanoic Before it breaks down, there's no ions present. It's just pure methanoic acid. Okay? But they tell us it breaks down and gives a concentration of H plus of 4.2 times 10 to the negative 3. So my H plus is 4.2 times 10 to the negative 3. Because it's a one-to-one relationship, I also therefore know my methanoate ion is 4.2 times 10 to the negative 3. Now, how did I get from 0 to 4.2? I must have added something. Same thing, how did I get from 0 to 4.2 for the methanoate? I added something. Over here, if I added something to increase my product, I must have lost the same amount to get to my new reactant. I know it went from 0 to 4.2. The X value must be 4.2. I started at 0.1 for methanoic acid, but then 4.2% of it ionized, and that's where I am now left with a concentration of 0.0958. So I put products over reactants, and I can get my Ka value. Now, I did not show you that here, but you would have 4.2 times 10 to the negative 3 squared, because it is your, is your concentration of your reactants, your products. There we go. Over the concentration of your acid, which is 0.0958. And that's going to give us our Ka value. And this was actually one of the questions from your textbook, so you can triple check and see what the answer is in your textbook. And let me just draw in a beautiful little line here to complete that and put in my equal sign. Okay, so this is question 22 on page 611. Okay, so, oops, well, isn't that awkward now? X. Even with all the mistakes I'm making in this video, this is far better than the one I made earlier today. Sorry this is so late. I did start nice and early, but I was not happy with the results. Anyway, so your homework for tonight, Monday, May 4th, 23 through 29 on page 611. And please, 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 please take the time to go back and watch this 13-minute video. I will put that under posts, so you can just click it and not have to go through a PDF and copy the URL and etc. etc. Okay, so again, we've started our acid base unit. You have this for homework due before Wednesday, our next class, and you also have a multiple choice assignment that I posted under assignments, and it's due Wednesday, and that's the last Q credit assignment, whatever, for equilibrium unit. So your homework for Wednesday, and then you have a credit assignment due Wednesday as well, and it is on equilibrium unit. There we go. And I'm trying to get in the habit of doing CR in red so it sticks out for you, so you know that matters. Alrighty? Okay, thank you. Happy rainy Monday.